I'll talk about, thank you for inviting me here. I will talk about joint work with Jovlen about the tropical one-fold Abel-Prym map. I will introduce and recall maybe some definitions in the tropical setting, but I would like to give some motivation first, and it comes from algebraic geometry. We start with the étale double cover of curves. We can consider the norm map, which is essentially the map from the Jacobian of the curve to the Jacobian of the target curve. And we define the prime variety associated to this étale double cover to be the kernel of this map. So here we just push forward the divisors under the étale double cover, and we define the prim as the kernel of the map. And we define the default Abel-Prym. Sorry? Yeah, we take the one that has the identity. Maybe I will put a 0 here. And we define this map to be from the symmetric product of the curve to the prim. So I'm introducing this object because it's actually the target of this map. And this sends a divisor d tilde to the divisor d tilde minus iota d tilde, where iota, I will put it here, is the involution of the double cover. So here we have a double cover. Iota will be the one that swaps the two fibers in the curve C. Okay, so I defined the prime variety and the Abel-Prym map, and there are classical results given by Birkenacke Lange and Casalaina Martin. About computing the degree of this map. If we consider the one-fold case, so where d equals 1, the degree of this map is 2 if and only if the source curve, so the double cover, is a hyperelliptic curve. And it is injective otherwise. If we consider d less or equal than g minus 2, then the degree of this map is 2 to the power of n, less or equal than to the d. Yeah, sorry, I didn't say it. D is the genus of this curve. And the degree will always be less or equal than 2 to the d, and the equality where n is an integer less than d, and this equality holds when the curve is hyperelliptic. Equality for hyperelliptic curves. I'm separating these two cases because this case was proved by Sebastian in characteristic 0, and he also extended it in characteristic P with one similar formula. And this is given by Birkenacke-Lange in their book. And for D equals G minus 1, the degree is always 2 to the G minus 1. So it's always the maximal one. Okay, so in the algebraic setting, we have already the computation of the degree, and we have this corollary by Birkenacke-Lange that for D equals 1, if the curve is hyperelliptic, then if we look at the image of this map inside the Prym, so I will call it delta D of C tilde, this is a smooth hyperelliptic curve. And the Prym variety of the double cover is exactly the Jacobian of this curve. So it's the Jacobian of the image at D equals 1 of C tilde. So what they proved is that the image is again hyperelliptic, and the Prym variety is none but the Jacobian of the image of the curve. So starting with this situation in algebraic geometry, we would like to do the same in tropical geometry. So we would like, sorry? They proved that if we start with a smooth hyperelliptic one, the image is smooth. Yeah.
Only in that case, okay, I see that.
So we would like to try and compute these results in tropical geometry in the tropical setting. So we will, instead of talking about étale double cover of curves, we will talk about free double cover of metric graphs. We will define in the same way the norm map, the tropical Prym variety. We will define the Abel-Prym map in the tropical setting. And then I will tell you which of them are already new or what we did in the paper. So I will write here. How does it work? I mean, I can do this. Okay. So in tropical geometry, we will have a free double cover of metric graphs. And later I will introduce a metric graph, a harmonic morphism, everything. I will just give you the results first. Free double cover. We consider the norm map. In the same way, we can define a Jacobian of a metric graph. And here, this map is also the push forward. We can define the Prym variety associated to this cover, which is the kernel of this map that contains the identity. And we can define the default Abel-Prym map in the exact same way. So it goes from the symmetric product of the metric graph to the prim, the tropical prim, and it sends a divisor of degree d to the to the divisors linearly equivalent to d minus iota d tilde, where again iota is the involution that swaps the covers. Same situation, iota involution. Okay, and results that are already known by Len and Zakharov. They studied the case d equals g minus 1, and they proved that for d equals g minus 1, the tropical Abel-Prym is a harmonic morphism of polyhedral spaces and has the degree that we are expecting. And motivated by this similarity in this case, they also wrote this conjecture in the same paper by saying that the degrees of the algebraic prim and the tropical prim coincide for each d. So the degrees of the algebraic and tropical coincide for the less than g minus 1. And what we did in our paper was considering the case d equals 1.
That's like curiosity. I don't know if this is maybe off the level, but why do you only look degree up to g minus 1? Why not like g?
Yeah, the bound is g minus 1.
This is to have minus value.
Yes, yes, exactly. Yeah, in this case, that's the limit. And in this case, these two spaces as polyhedral spaces have the same dimension in g minus 1 case. And yeah, what we did was considering the degree, one-fold Abel-Prym, and we proved that actually one of this is true. So if C is, if gamma tilde, if the graph is hyperelliptic, then the degree of the map is 2. But we don't have the opposite. We have a partial converse. Only if the Abel-Prym map is also finite, we get hyperellipticity. So if psi is finite harmonic morphism. Okay, I will switch the boards. Morphism. of degree 2, then gamma tilde is hyperelliptic. We found counterexamples of non-hyperelliptic graphs where the Abel-Prym map is not even harmonic, so we can't define the global degree in general. But if we assume that psi is finite, and I will tell you what finite means for a harmonic morphism, then we have the opposite. We have also that the gamma tilde is hyperelliptic. And as a corollary, we proved that also in tropical geometry holds this statement. So we proved that if we consider gamma tilde hyperelliptic, then the image is a hyperelliptic graph. Corollary. And the same with the Prym variety in the Jacobian holds in tropical geometry. The image is hyperelliptic. And the Prym of the cover is isomorphic to the Jacobian of the image. And this isomorphism here, we proved it as principally polarized tropical abelian varieties. And I will tell you later what's the structure of the tropical Prym and the Jacobian as real tori with integral structure, and how we proved this isomorphism. Okay, so today I will basically talk about these two results. But first, I would like to introduce some basic definitions. It's stuck. Okay. What?
Put in the middle of the board is easier.
Like this?
Center of the board. Like here.
Ah, yes, thanks. Yeah, okay. Okay, so just a bit of introduction. Recall. We will consider metric graphs. So whenever I talk about metric graphs, I have a graph G together with a length function on the edges. And that's the model of our graph. And I will introduce the definition of harmonic morphism of metric graph. I will start with an example. For instance, suppose you have this graph. In order to have a metric graph, we have to assign lengths of the edges. So I will assign here the same length, here B and C. And I will define this morphism. Here, I will send these two vertical edges on the vertex. These two edges I will identify here as one edge. But the harmonic morphism can also stretch one edge. And here I will identify these two, and those two edges get contracted. So usually in the harmonic morphisms, we can have a dilation factor. I decided that this is a 2, and we can also get two edges contracted to a vertex. So it is a morphism of graphs, but there is also another condition on the length, that if the image let's call it E prime, then has to be true that L prime, so the length of E prime modulo the length of E is an integer. Okay, for instance, here we have a dilation of a factor of 2.
Oh, sorry, this is for
Yes. And we call this slope of the map. And now I will introduce what's harmonic. So we will say that phi is harmonic if the following holds. So basically, we need to check at every point if the preimage is, I mean, for each direction, we have to have the same number. For instance, here we have 2 preimages, but with the same length. On this side, we have 1 preimage, but of multiplicity 2. So on each direction, this number that I'm writing here is 2 for each vertex in G. So let's call it phi is this morphism. We have to count overall edges of G. The slope of the map. And that's called the multiplicity, horizontal multiplicity of the map. So here the slope will be 1 or 2, depending on if we have dilation or not. And we see that we say that phi is finite if this number is always non-zero. What does finite mean? There are no edges that are contracted to a point. Because here, if we assume greater than 0, we don't have like infinitely many points in the same fiber. And that's also the problem here. And I will tell you at the end of the talk why we found a counterexample where phi is not finite. And the degree is the sum of the multiplicities of phi is sum over all edges and obviously this has to be the same for all choices of E prime. And also the degree is well defined. It doesn't depend on the choice of the edges. And a harmonic morphism is free, and we will use it later. And we will use it of degree 2 if the preimage of every point has exactly size 2. So in the free case, this dilation doesn't happen. So in the free case, we always have the preimage as 2 distinct points or 2 distinct edges. And we will restrict ourselves to 3 double covers of metric graphs. And a double cover is a morphism, harmonic morphism of degree 2. I can also draw an example, for instance, this one. The double cover of the dumbbell graph is a free morphism, harmonic morphism. You see here that for each edge, we have exactly two distinct edges. Also for the loop, we have two distinct edges covering the edge. And I will talk about now, I will introduce the Prym and the Abel-Prym map and talk about the hyperlytic case. Prym varieties. So I introduced the harmonic morphism and the dilation factor because even though we start with a free double cover of graphs, the Abel-Prym map will be harmonic of degree 2. So there will be dilation. Where did I write it? Yeah, I will also write it. This map will be harmonic of degree 2 with dilation, with edges contracted and edges mapped injectively. So we have free double cover. And the one-fold Abel-Prym will be from the graph gamma to the Prym, sending 1 point to the class of P minus iota P, where iota is the one associated to the cover. And yes, I have it here. Usually when we have free double covers, the kernel has two connected components. One is the even and one is the odd Prym variety. We will consider the even Prym variety, but in our case, we will have this torsor because this is odd, the odd Prym variety. But we will consider just as a definition this Prym variety. And I will give you some properties about this. Because as I was saying earlier, there are some edges that get contracted, and there are some edges that get dilated. And in which case, so if we consider E an edge downstairs, and we consider E prime, second prime, in the preimage of E, then the following situations can happen. First of all, the Abel-Prym map, I will call it AP map, contracts all bridges of gamma tilde. So if gamma tilde is a graph with bridges, it contracts it. And that's because here we consider all the points linearly equivalent to the point that we are considering. And on the bridge, all the points are linearly equivalent to each other. So they go to the same, they are in the same fiber. But if E is not a bridge, and these two edges are such that gamma tilde minus E prime in second prime is disconnected, then the Abel-Prym map contracts. And that's a result of Len and Zakharov. So also in this situation, if E is not a bridge, I can also draw a picture. So E is not a bridge. and the preimage disconnects. Okay, so if this is E, this is E prime. These are the two preimages of the loop. We don't have a loop downstairs, but gamma tilde minus these two edges, it's disconnected. And here we can find infinitely many divisors linearly equivalent to each other on these two edges, and also on the bridges. So the Abel-Prym map contracts the bridges and also these two edges. And since we will use them again, we will call them properly disconnecting pairs, meaning that without one edge, it doesn't disconnect the graph, but two of them disconnect the graph. E prime and E second prime are called properly disconnecting pairs. And there's also another property. Now, the case where E is a bridge. And we have the preimages that are properly disconnecting. Then the Abel-Prym map dilates them by a factor of 2. So these edges get dilated. I mean, this situation. Downstairs is a bridge, but upstairs is not a bridge.
So there in number one is.
In number one is, yes, is all the bridges that you have upstairs. Here we have this situation, so we have a bridge, but the upstairs they are not a bridge, but they are properly disconnecting pairs. And in the by the Abel-Prym they get dilated but mapped injectively. So they are dilated, but it's injective on those edges. And as a remark, if you prefer more the matroidal perspective, there's a paper by Felix and Dimitri, and they gave to the tropical prime variety a matroidal structure. And these properly disconnecting pairs are the one circuits of that matroid. So properly disconnecting pairs. Of the matroid constructed by Felix and Dimitri. So all of the properties that we proved by using linear equivalence of divisors and using this approach can also be proved by using matroid theory. Okay, now if you don't have questions, I will go to the hyperelliptic case. So what will we do will be state this theorem about the hyperellipticity and do the corollary of the principally polarized tropical abelian varieties. I can erase also this one, right? So that was just the motivation, and we already proved that this is not happening in tropical geometry. So I will give you a counterexample. Sorry. Thanks. And before stating the theorem, I will introduce hyperelliptic graphs. And then I will tell you how to construct and how to compute the degree of the map. Okay, so the definition of a hyperelliptic graph is the same as in algebraic geometry for hyperelliptic curves. And I will give you also a metric condition, which is better to use. So we say that gamma metric graph is hyperelliptic if there exists a divisor of degree and rank 1. But we can also describe the hyperellipticity by the existence of a length preserving function from gamma to gamma. It's an involution on gamma such that the quotient by this involution is a tree, is a metric graph of genus 0. For instance, if we consider this graph, we either can find the degree 2 and rank 1 divisor, or we can find an involution such that the quotient is a tree. So for instance, the involution sends this point to this point and so on. And actually, this equivalence is proved in this way. By starting with the divisor, we can construct the hyperelliptic involution. And we proved that if we consider a double cover where gamma tilde, if gamma tilde is hyperelliptic, then also the target graph is hyperelliptic. And the following diagram commutes. So if we have gamma tilde with the hyperelliptic involution gamma tilde, we have the double cover pi, that was the free double cover that we were talking earlier. And we have here the hyperelliptic involution. This diagram commutes. So basically is the same as in algebraic geometry, that if we have a hyperelliptic curve, then by push forwarding this divisor, we get a hyperelliptic curve downstairs. And actually the proof, show the proof. We used the properties of harmonic morphisms, because harmonic morphism send equivalent divisors to equivalent divisors. Equivalent. So if we consider, so if we assume that on gamma tilde we have d tilde, if we consider the push forward, this is a divisor, of degree 2 and rank at least one, and then by tropical Clifford we get that it has to be exactly 1. We have a degree 2 divisor and the rank is exactly 1. And the commutativity, we used the structure of the two involutions and we proved that in all the cases they commute to each other. For instance, that's a hyperelliptic graph. And you see that the bridges are fixed pointwise by the involution. This one, yeah. If you push forward the G12, you get the G12 downstairs, yeah. I don't know. You mean the commutativity? Yeah, we don't know. I don't know. And since we know that by starting with a hyperelliptic one, we get a hyperelliptic double cover, we also we can start by constructing hyperelliptic double covers by starting with the gamma downstairs. So we constructed hyperelliptic double covers because the opposite is not always true. So there are hyperelliptic curves, but there are non-hyperelliptic covers. So we constructed the hyperelliptic ones. We used the fact that by tropical Riemann orbits, if we have a graph of genus G, then the hyperelliptic involution has G+1 fixed points. And by, for instance, in this case, and by studying the fixed points, we were able to construct all of the hyperelliptic ones. And as a result, we have G+1 hyperelliptic covers out of 2 to the G-1. By construction by Len and Zakharov, given a graph gamma, we can have 2 to the G-1 double covers, free double covers. And we counted the hyperelliptic ones. So there are G+1 hyperelliptic double covers. We're ready to state the theorem. If we start with gamma tilde hyperelliptic, then the map is a harmonic morphism of degree 2. And what we do, we actually observed that whenever we have a point, P, if we want to find another point in the fiber, this is given by using the involution. So if we consider this point, and then we take the hyperelliptic involution on this point, and then we take the double cover involution, then we found that P minus iota P as a divisor class is equal to Q minus iota Q. That's basically playing with the two divisors and using the construction of the hyperelliptic involution. And that's basically also the algebraic proof by Birkenack and Lange. So they proved that the fiber over some points has exactly two distinct points. But in algebra, in tropical geometry, sometimes Q can be not different from P. For instance, in this case, if I take P here, I told you that the involution, hyperelliptic involution is this one. So J tilde of P will be this point. But iota is also this involution. So iota of J tilde of P coincides with P. So in this particular case, we have 2 points, but they coincide. So a priori, we could have degree 1 Abel-Prym. But we proved that on those points that we have like P and Q equals, the Abel-Prym map actually dilates those edges. So if you remember, I told you that the harmonic morphism doesn't have to be always 2 sides with the fiber, can also be dilation. And in the dilation case, we have 1 preimage. So we have 2 points, but they are the same point. So in order to prove that psi is a harmonic morphism, we have to prove that on each point in the image, the preimage is either 2 distinct points, P and Q different, or they coincide and the length, the dilation factor is 2. And also there are some points that are contracted, and we have to check also that part. So we constructed psi by using these 2 involutions, and actually we could also have a description of the image, because the Abel-Prym map is going on the Prym variety, but the image is a graph. And as a result, the image is isomorphic to the graph gamma tilde modulo iota cert J tilde. So we proved that if we take the quotient graph by these 2 involutions, we get the same as doing the Abel-Prym map. So we proved that all of these edges are exactly the edges that we compute when we take the quotient. And taking the quotient is easier, and you could do it also in that example. What's the image of the Abel-Prym map here? This edge is identified with this edge because a point here, P, has J tilde here. And then iota is going here. Iota of J tilde of P. So whenever we take a point in this edge, we find another point in the same class. So we are identifying those 2 edges. On these 2 edges, the Abel-Prym map dilates them. So they're going to be by a factor of 2. And here they are, again, this. So you can see that the image is this graph. And it's obtained by taking the quotient. And in order to prove this, we showed that by taking the quotient, there are some edges that are flipped, some edges that are fixed, and they coincide with the quotients, with the edges in the property of the map. Okay, if you don't have questions, I will talk about principally polarized tropical abelian varieties. Yes.
That you have no dilation, right? If you're lucky, maybe.
Yes.
And
The
then you can play this game again, right? Because then you, by your proposition, you have a 2-to-1 cover then from gamma tilde to this quotient,
image, yeah.
and that's again hyperelliptic,
Yes.
and you can play this again, right?
Yeah, in
You
that
have
case,
a new Abel-Prym map, right?
yeah, because it will be like a free double cover of two graphs, and you can, yeah. No, I haven't considered. So the thing is that you get dilation only if you start with a bridge. So if you don't start with a bridge, and the pre-images are not bridges anymore. So if you don't start with this bridge, you don't have dilation.
So it probably has to stabilize at some point.
So if you have like, if you have two edge connected graphs, yes, you can go on and on. Yeah, because that's the only case where we have dilation. And we are left to prove the corollary on the Prym variety and the Jacobian from the tropical point of view. So we proved that the Prym of the cover is isomorphic to the Jacobian of the image. And I will now tell you what the structure of the Jacobian and the Prym as real tori looks like, and how we prove this isomorphism. So the Jacobian is given by these two lattices. It's the one forms of the image, gamma tilde is H1 of the image, and the intersection pairing. I will also explain how to construct the intersection pairing. The Prym is given by two different lattices, the co-kerr torsion field part of the co-kerr, the kerr, kernel of the map, and an intersection pairing that comes from the Jacobian. So essentially, if we want to compute the intersection pairing, if we have a one form and a cycle, the intersection pairing is, the one form will be sum of some coefficient BE, sum of BE, E, integer. Then you take, in order to construct this, you take the homomorphism here real, and then you quotient out by this one. Yeah, these are the two lattices, and then you take home of this. Yeah. And okay, so you define the intersection pairing to be the intersection of the one form on this cycle, which is the sum of this coefficient times the length of the edge. So you take the coefficient and then the length of the metric graph. Okay. And in order to show a isomorphism of principally polarized tropical abelian varieties, we need to show that there is an isomorphism and the diagram commutes by these two lattices. And then we also have to check that the two integration pairing commute, like that they're well defined. And what we do, given our construction of the hyperelliptic covers, we also have a natural basis for the H1. So we have a basis of cycles. And we use that basis of cycle in order to prove. And also we use the fact that the image is exactly the quotient graph. So we can use that part. So, okay. So we proved that if we start with the coker, we have a map here, upper hash from H1. We have the other lattice here from H1. And here we have the two principal polarizations. This is a lower hash. So a basis of the kernel is given by anti-symmetric cycles that I will draw in this way. So we take a cycle minus iota of the cycle, and we send it to the image under the Abel-Prym. Sorry. And we proved that the image of these cycles is exactly a basis for the image for this Abel-Prym graph. And here we took basis and we sent it to the class of this modulo symmetric cycles. And then we have to prove that by taking the intersection product of cycles on the Jacobian is the same as taking the intersection product on the Prym. And maybe if I have time, do I have time? No? Yeah, no, I just wanted to show you an example of the construction of the basis. Because we start with the double cover, and we start with this curve, hyperelliptic curve. For instance, we have this double cover. What I want to say is that we can start by taking a basis of cycles here, then leave them as a basis of cycles upstairs, and then apply the Abel-Prym map. Okay, something like this. And the Abel-Prym map is the quotient graph by the two involutions. Which is this one. So it holds this graph and the quotients. Sorry. This graph, this edge, it gets in the same class as this one. So it's like in the opposite folding. What we did was finding a basis of cycles here. For instance, cycle is given by this one. We take the pre-image, so it's this cycle, but also iota of this cycle, so it's this one. And then we pushed forward here by this map, but this gets identified with this one, and it's this cycle. So you see, since we said, I mean, we can also start from here in some way, and by this cycle, we have this cycle. There is some problem with the bridges that we have this situation here. And yeah, we characterized this because here we start with a genus G graph. The image is always G minus 1. That's only in the hyperelliptic case. In the general case, it's not this. And what we said, I mean, what we found out that is that if we have two cycles here, since the genus has to drop by 1, this cycle, these two cycles get identified by this cycle. And it comes from this and then taking the image by the Abel-Prym. But yeah, sorry if I bit over time. There's also the non-hyperelliptic case. I just said that it's a bit different, but we just have in the hyperelliptic case this nice structure, and we can compute the image and the Jacobian and the Prym, but in the non-hyperelliptic case, it's not. Okay, thanks you so much.